Welcome back, students. Yesterday we were discussing nuclear cross section, and in nuclear cross section we discussed this excitation function, which was actually the relationship between energy of the bombarded particle and cross section. And you know what cross section is. So cross section is the area being provided by a nucleus for a nuclear reaction. In this case, the cross section was sharp, and also in coming slide we are going to discuss it in detail. There is another graph. This also has been adopted from the book which you already have. Here you find these dashed lines. So these dashed lines are threshold energies, calculated energies for the nuclear reaction, and a reaction for thorium in four different styles or four different reactions for thorium 232 have been shown. This indicates the first reaction, that thorium being bombarded by alpha particle where a neutron is produced. In another reaction, two protons are produced. In next reaction, three, and finally four neutrons are evaporated. So this is the threshold limit of energy as well as the cross section. So if you look at the cross section, so for fourth reaction, what we expect that the cross sectional area would be the same, while energies, threshold energies are different. In this case, the energy is around 10 mega electron volts. Here it is more than 15 electron volts. Here it is around 25 mega electron volts, and here then it reaches 30 mega electron volts. Now, and this is the classical barrier or Coulombic barrier of the nuclear reaction. Now, in first reaction, actually what happens in this case, this is the reaction where alpha particle has been bombarded on thorium and one neutron is evaporated. So the cross section of the reaction or the nucleus is less. Now this cross section increases if we increase energy. Here energy is in the range of 21 to 22 or something like that, but here energy is now more than 25. So if we increase the energy of alpha particle, what happens, the cross section of the target nucleus increases. For another reaction, then this is the maximum cross section or this excitation function for this reaction where three neutrons are evaporated, and for fourth reaction, then the excitation function again it decreases, and the area being provided by the nucleus for nuclear reaction is again less. So in this case we can predict theoretically as well as experimentally which reaction will be more feasible, what type of or how much energy is needed, and what type of reaction will be more if more than one reaction occur, what will be the highest product in case of these four reactions. So this reaction is the most probable and feasible reaction provided that energy in this range is provided to the nucleus or bombarded nucleus. So this was all about cross section. Now coming to a direct reaction or direct interaction. Now we have already discussed the combined nucleus theory, and in this combined nucleus theory what happens whenever a particle is bombarded on a nucleus, so nucleus interacts as a whole with that bombarded particle, and this interaction is in terms of absorption. Whenever we bombard a nucleus by a particle, that particle gets inside the nucleus, the target nucleus, and we expect that overall the nucleus interacts. And whenever this nucleus interacts with the bombarded particle, so what happens? The nucleus becomes deformed, and this deformation then comes to regular shape or spherical shape. It will rearrange itself towards stability, and whenever it goes towards stability, so some of the energy or excess of energy will be evolved, and that energy is evolved in the form of certain particles to be evaporated, and this process is called disintegration. The only point in this case, in the case of combined nuclear theory, it was the interaction of the nucleus as a whole. So, in this case, now if we increase the kinetic energy of bombarded particle, so what happens? Emission of high energy particles are absorbed. In this case, in combined nuclear theory, slow moving particles were absorbed, while in this case, high energy particle will be absorbed in case of the bombarded, the more bombarded kinetic energy. Now, what does it mean, or what type of particles are produced? Neutron as well as protons are produced, and this cannot be explained by this simple combined nuclear theory. So this is because that the cross section is much more larger than the expected value. If we calculate the cross section for the reaction, then the value what we expect is much more than the calculated one. Now, in a general reaction of type A, where A is bombarded by a high energy proton and C is produced along with a proton and neutron. Also, we will represent this reaction in next page. So this is a general reaction, and several particles up to 7 are produced in order as to de-excite the nucleus. Now, in this reaction, the particles other than neutron, this cannot be explained by simple this combined nuclear theory. Then R. Serber, he proposed another theory as well as a mechanism of this reaction, that how this disintegration proceeds. Now deuteron protons are alpha particles up to 50 mega electron volts when they are bombarded on a target nucleus. So successfully, this theory explains that how particles with high energies are produced, and these reactions then proceeds in two steps. Now, in first step, what happens? Direct collision of bombarded nuclei with individual nuclei. For example, inside the nucleus there are too many neutrons and protons. So the bombarded particle, whether it is proton, neutron, or any other heavier particle, it interacts directly with an individual nuclei. It interacts with a single neutron or proton inside the nucleus. And what happens? Whenever it interacts with an individual nuclei, that individual nuclei is struck out of the nucleon. So, in this case, the struck nuclei and bombarded nuclei both, they have equal probability to escape from the nucleus. For example, we are bombarding a nucleus. There are neutrons and protons. They struck nuclei. What happens? They struck nuclei. The bombarded nuclei struck a nuclei. Let's suppose that is proton. So proton is kicked out from the nucleus, and the bombarded nucleus also gets the same probability to escape from the nucleus. So both the particles, the bombarded particle as well as a neutron which was already present in the nucleus, they leave the system or they leave the nucleus. If they both escape, the residual nuclei gets very less energy. So there is remaining energy of residual nuclei, although some of the kinetic energy has been transferred or shifted to the target nucleus, and this target nuclei is now gaining less amount of energy because most of the energy has been taken away by an evaporated high speed proton as well as neutron. So the escaping of high energy proton and neutron now can be justified, that how that takes place. Second step is, if both of these particles they remain in the nucleus. For example, we are bombarding a nucleus with a particle, and that particle gets absorbed inside in the nucleus. Now what happens? The collision with other nuclei also gets a chance, and this possibility of collision with other nuclei, it starts or initiate a process, and that process is called knock-on cascade. This knock-on cascade process results into evaporation or emission of more than one particles from the nucleus, because The interaction of nuclei gets considerable time, and this time is in the range of 10 raised to the power minus 19 second. So in this case, more collisions are possible. Collision can be one or can be more, but this second step we have to